This video is about sampling methods in statistics. A simple random sample, which we will often call an SRS, of size n, is a sample from the population that's selected in a way so that the following two criteria are met. Every member of the population has an equal chance of being selected, and every sample size of size n has the same chance of being chosen. So, for example, in our class, if we have 32 students, we could write everybody's name on a piece of paper, mix them all up in a hat, and pick four people's names. That way, everybody has the same chance of being chosen, and every possible group of size 4 has the same chance of being chosen. I could also do the same thing in, like, I could use a roster, the class attendance sheet, number everybody 1 through 32, do a random number generator, and select the sample that way. Um, When choosing a sample, occasionally the same number is going to be selected twice. However, most of the time we don't want that. We want to sample without replacement because we don't want the same person showing up twice in an interview or something like that. We want to get a little bit more variety. So we often don't replace. Some advantages to simple random samples: it's simple, it doesn't require much foreknowledge, preparation. Pretty much everybody knows how to put everybody's name in a hat, and it's random. We get the randomness we want because when we have randomness, that reduces the variability that can occur if things aren't random, um, or it can reduce bias that happens when things aren't random. But there's some disadvantages. Sometimes it's impractical or hard to do for very large groups. So, for example, if we are doing political polling, Um, it's hard to do a simple random sample of the entire state of Illinois if we're trying to figure out who's going to win a presidential election or a governor election, gubernatorial election. It's hard to do a simple random sample, um, because even if you go through the phone book, which people don't put their phone numbers in a phone book anymore, even if you do something like that, um, it's very hard to figure out if you have everybody in the phone book. Um, so it's hard to get the entire population in a simple random sample where you just randomly select 100 or 500 or something like that. Same thing if you're trying to do our entire school, it's hard to randomly select 100 people from our school and actually get information because then you have to find a way to get that information maybe to each kid in their classroom, and uh, just sometimes it's logistically very hard. It's also possible that we end up with a sample that doesn't represent the population very well. So, back to using our class. If the classroom that our 32-person class is is the population, and we randomly select four people, and all four of those people are girls, and the question is dealing with how much money you spend on preparing for the homecoming dance. Um, it's possible that those four people that were selected may not represent the population of our entire class because it's very possible that the amount of money that you spend getting ready for homecoming could be dependent on gender, um, just based on how much dresses cost versus how much a suit or a shirt and tie cost, plus the amount you have to spend on flowers or dinner or something like that. Gender may play a role in that. And so uh, sometimes simple random samples don't actually represent how much the average person in the class would spend on homecoming or whatever the question may be. So suppose that a class is half boys and half girls. To get a sample of size 4 from the class, we could also get a random sample by writing the name of every boy on a piece of paper, putting them in a separate hat from all of the girls, mixing both of them up, and picking two names from each hat. It's not a simple random sample because not every group of four has an equal chance of being chosen. So if you're looking at this situation, there's no possible way that I could get a group of 4 girls or a group of 3 girls and 1 boy. So all of those groups have 0% chance of being chosen. Not every group of 4 in the entire class has the same chance of being chosen. So it's not a simple random sample, but it is what we call a stratified random sample. A stratified random sample is a method of random sampling that tries to reduce the variability that's given in a simple random sample because we pick subgroups that may have an impact or an influence on the question that's being asked. So we want these stratum, plural of stratum would be strata, strata. So each subgroup or strata, we want them to be properly represented. So if our class of 32 people was 24 boys and 8 girls, for example, and we were asking the homecoming question, we may want to put all 24 of the boys in a hat and all 8 of the girls in a hat, and then randomly select 3 boys and 1 girl to proportionally figure out uh, what the average, just a sample average amount spent on homecoming would be. Um, so what we want to do is we want the members of each stratum to be as similar as possible with regard to the question of interest and very different from members of the other strata. So if we think that gender or um, something like that would make a difference in terms of how much money you spend on homecoming, then you would want to stratify by gender, um, keep the genders separated, and pick a proportional amount in each gender. So this sample problem that we have, if we assume there are 600 freshmen, 500 sophomores, 500 juniors, and 400 seniors, and we wanted to ask a question about assemblies, it may be a little bit different based on how old you are. And you are a senior, so you've had more experience with assemblies, and you think they're good or you think they're bad. And freshmen might just be excited because it's their first assembly at a high school or something like that. Just there might be some differences based on class. And so if we want a size of 100 in this sample, if we look at this, we have 2,000 students at the school. And so if we have 2,000 students and we want a sample of size 100, that means that we have to take 600 out of 2,000 freshmen. So 600 of the 2,000 students are freshmen. And so we want 6 divided by 20, which is 3 divided by 10, or 30% of the representative sample to be freshmen. So what we would do is we would take 100 and multiply it by the percent of the population that is in each category. So we want 30 freshmen. Likewise, we have 500 sophomores and juniors. So if we take 500 divided by 2,000, that's 0.25. So we have 100 people in our sample, and we want 25% of our sample to be sophomores and juniors. So we have 25 sophomores, and it accurately represents the class breakdown of the school. Now, before we move on to this corn example, it's kind of important to understand that just because I sampled 100 people, that does not mean that I get the accurate feelings on the assemblies of everybody in the school. But the bigger my sample is, then the better off it ends up being. But oftentimes, money or time makes it hard to actually ask all 2,000 people in the school. So you pick a sample that you hope represents the population, and you get one shot at it, and you hope that that sample ends up giving you an accurate picture of what's happening. So suppose we want to estimate the yield of this cornfield. So this farmer has a cornfield. The field is square, and he divided it into 16 equally sized plots, and a river runs along the eastern edge of the field. We want to take a sample of 4 of these plots because he doesn't really want to uh, analyze or count all of the yield. He just wants to get an estimate so that he can figure out how much he will be able to sell his corn for this year, whether he's going to have to uh, figure, how much corn is he going to get? Is this going to be a good year or a bad year? He's just going to try and figure it out. And so, what we want to do is um, we want to randomly select 4 of these plots, and then we will just count how much corn is in each of the plots, and then we'll divide it by 4. We'll do a simple average, and then we'll figure out what the yield is, or what our average, estimate is, and then we'll eventually figure out what the total average corn yield is in this situation. So I'll make sure that we know how to use a random number generator on the calculator. So if we go to math and then scroll over to probability, we have some random number generators on the calculator. You can also get these on the internet. Just Google random number generator and you'll be able to do this. So I'm going to want random integer, no repeats. My lower number is 1 and my upper number is 16 in this case. I want to have 4 numbers that come up. And so I randomly select and I get 7, 15, 11, and 10. So that means that 7, 15, 11, and 10 are going to be the squares that I actually pick. And when I look at this in a little bit, I'll figure out how much corn that I'm going to estimate that I have. So what you may notice about this is that it's possible to get a variety of things. You could have 4 squares all far away from the river. You could have, in another sample, 4 squares all really close to the river, or any combination thereof. And it may be important to understand that the river might have something to do with how good your corn is. So a simple random sample may not be the best way to do it, but we'll do that and figure it out. Now we can also stratify by row. So what we could do here is we can stratify by row. So I will select 4 random integers. So I'm going to go to the random integer generator. I don't mind having repeats here. So my lower number is 1 and my upper number is 4 because as I counted all of these, they were all 1 to 4. And I want 4 of these numbers, and it doesn't really matter what numbers I get. So 3, 4, 2, 2. So if I look at this, 3, 4, 2, and 2. So this is what happened when I stratified by row. So basically, what I said was I'm only going to take one of these 4, one of these 4, one of these 4, and one of these 4. Once again, notice I still possibly could have got 4, 4, 4, 4, and that would mean that I would have all of them by the river, or I could have had 1, 1, 1, 1, and they would have all been far away from the river. Now, the last option that we have is stratifying by column. Now, if I stratify by column, basically what that's saying is I'm only going to get one of the 4 in each of these 4 columns. What that's going to guarantee me is that I get one close to the river, one far away from the river, one that's sort of close to the river, and one that's sort of far away from the river. So if I randomly get some other ones, 1, 4, 3, 2, but in the interest of just showing you, it doesn't really matter what numbers I get. Let's say 2, 4, 3, 3. So I randomly selected again. That's bad. You should not do that. Whatever you get, you should take. But I'm just going to take the second one that I got, 2, 4, 3, 3. So if I take 2, 4, 3, 3, 2, 4, 3, and 3, notice I got one plot far away, one plot close, one plot sort of close, one plot sort of far. So this random sampling method, stratifying by column, ended up being probably a decent amount, a relatively effective way. And I would say stratifying by column would probably be the smartest way to go about this. I calculated all of the averages for the samples that we actually got, And if the farmer took a simple random sample and got the exact numbers that we got, he would assume that he got 78.5 um, is his average corn yield. Um, that would be his assumption because he would only be taking one sample. It's not like he would be taking a whole bunch of samples. He gets one shot at it, and that's what he gets. Stratified by row, he would have got 76.5. If he got the exact same numbers that we got when he stratified by column, he would have surveyed this square, the 92 square, and the 148 square, and he would have got 69.75. So that's what he would have got. Um, Again, it's important to know that when you take a sample, you're only getting one shot at it. And so if the person got a simple random sample and it just so happened that they got 94, 153, 148, and 147, he would think he has way more corn than he actually has. So that's something that's really important to keep in mind, that your sampling method, you want to reduce variability as much as possible because you only get one shot at it. Now, if we take a look at what happened, if you actually calculated the entire plot's mean, it would be 70 per square. But clearly, it's very different based on where you are. The closer you are to the river, lots more corn. Further away you are from the river, much less corn. So, what I did, and you'll be seeing this on the screen, is I did 30 simple random samples. And all of the values for the simple random samples are in X1. I stratified by row 30 times, and I stratified by column 30 times. And so all of these numbers represent what happened when I just wrote a program and basically did that. So if I had a simple random sample and I did this 30 times, not counting the one I did for you, but I did 30 more, I got a mean of 67.35, which isn't too bad. That's pretty close. And a standard deviation of about 23. That's pretty big. So if I just look at the dot plot and I take a look at the dot plot, see how spread out it is? It's very spread out. There are numbers that are as low as 34, number that's even bigger than 120. Um, and then I can take a histogram of that data and notice it's also very spread out. The data is centered around 70, or it's actually centered around 67, but pretty close to 70. So the mean is right about where it should be, but the variation is very wide. And again, just a reminder, if I change what a histogram looks like, the bin width can influence how my graph looks. Even if I changed where the bin was aligned, it would change how it looks. So that's just a reminder from last unit. If I stratified by row, notice it's still very spread out. My mean is still kind of close to 70. I got some low data points in this one, but if I did it 100,000 more times, I would be right around 70. My standard deviation is still very big, so I'm having some really small ones. I got a 17 in this case. I got two 109s. I mean, it's very wide. Histogram would also show the same thing. But if I stratified by column, notice what happens. Pretty much everything is right around 69, 70, something like that. Notice my mean is very close to 70. My standard deviation is very small. It's less than 1. And that's because if I look at this, all of the real low ones are over here. All of the kind of low ones are here. All the medium high ones are here. And all the really high ones are close to the river. And so if I structure my sample in such a way where I take one from each of these, I'm going to get something that's close to the actual mean, which is what I want. So what happened? We stratified by columns, the variability was greatly reduced, but every plot was centered in the same place. So, oops. So that's good. Um, we call that unbiased. So there's bias if the plots are centered in the wrong spot, and there's variability if the plots have a wide amount of variance or a wide difference in how close the data points are. Why does this work? With an SRS, it's possible that I choose 4 points near the river or 4 points far away from the river. But when I stratified by column, I was guaranteeing myself to get things that were kind of close to what the actual average was going to be. If I'm stratifying, or if I have some questions, like for example, affirmative action, a possible strata that might uh, actually be a good way to break up who you survey, like who you put in separate hats. Um, Race and gender would be really good. Um, those would be very good strata. Um, Age might be another strata. People of certain ages might find that to be something that's a positive thing or a negative thing. Their opinion on affirmative action may differ if you're older or younger. Non effective strata would probably be something like, um, what outfit you're wearing. You don't want to put everybody that's wearing a sweatshirt in a hat and pick names out, and everybody that's wearing a t-shirt in a hat and pick names out. That's not really relevant. Shoe size, not relevant. Um, Basically, things that don't really affect the question of interest, those are non-effective strata. Separating by things that do affect the question of interest, those are effective strata. Wabansie Valley High School option area. Should everybody be allowed to sit in the option area during lunch, or only juniors and seniors? Possible strata. Um, Grade level. If you ask seniors, they probably want to keep the freshmen out. If you ask freshmen, they may want to stay out, who knows, or they may want more freedom in terms of where they can actually go. Non-effective strata. Eye color would be an example. There are lots of different things that you can talk about as effective or non-effective based on how it affects the question of interest. So there are advantages to stratifying. It makes the sample more representative of the subgroups within the population, so you don't over or underrepresent people. And if strata are chosen correctly, it reduces the variability a lot. Um, Disadvantages: you have to know stuff about the population before you do things, and that can be very difficult. So you have to be able to, when you're sampling, if you want to stratify by race or gender or something like that, you have to know the races and the genders of the people before you actually start sampling, so then you can put them into different hats. You cannot just sample and then ask them what their race or gender is after you sample them. You have to make sure that they are separated at the beginning, and that's difficult. Some other sampling methods that we want to talk about: cluster sampling. This is something that often happens in schools. If you want to get some information on uh, on something like uh, how to, uh, if you want to figure out how freshmen feel about advisory, um, you could ask 5 advisory classes, because if you want to sample about 100 freshmen, you can randomly select 5 advisory classes, and then you are pretty likely to get a random sample of freshmen. But you also have to be careful, um, because cluster sampling is, it's possible that you can uh, overrepresent certain populations. For example, if you randomly select English classes and you want to select, let's say, 4 English classes to survey, you can't just put all of the classes in there and then randomly select 4. If you're asking for maybe an average GPA, what if all 4 classes you select all happen to be honors classes? Your average GPA will probably end up being higher than the actual average GPA of freshmen in the school. And so it's kind of important to make sure that when you're cluster sampling, you also keep in mind the fact that um, you might have certain uh, certain biases that may happen just because of the way the clusters are. Um, So cluster sampling involves dividing the population of interest into non-overlapping subgroups, which are called clusters. Clusters are then selected at random, and all individuals in the selected cluster are sampled. since whole clusters are selected, the ideal situation occurs if each cluster mirrors the characteristics of the population. This doesn't always happen, like in the example I just said with the English classes, because honors English classes and other English classes tend to not have the same population in terms of grade point average or something like that. And so you have to um, you have to try and choose as many clusters as you can afford, or you can also combine stratifying and clustering. Let's say there are 6 honors English freshman classes and let's say 12 non-honors English freshman classes, and I want to sample 3 classes. Well, I could stratify into honors and non-honors, and then I could select one of the honors classes and 2 of the non-honors classes. That would give me a proportional representation of classes, and then I want to sample everybody in the class. And so we just kind of talked about how would we choose clusters in the school. You have to be careful um, with how classes are selected. It's important not to confuse clustering and stratifying. If we stratify, we sample uh, a proportional representation from every subgroup. But in cluster sampling, we just pick certain subgroups and then everybody in that subgroup gets selected. Because of that difference, we want homogeneous strata and heterogeneous clusters. So we want people that are similar in some way that's related to the question in strata or subgroups for stratifying. But we want people that are just kind of general representatives of the population in clusters. And that's kind of hard, and sometimes we have to combine them to get as little variability as possible. Systematic sampling is another one. Um, as people leave the movie theater, surveying every 8th person to ask how the movie was. So that's something that works relatively well. You just have to be a little bit careful. You can't systematically sample. Let's say you want to figure out how many people are absent from school, and you do a uh, systematic sample where you just look at the attendance sheet and figure out absences every 5th school day. Well, that ends up giving you a lot of Mondays in a row, or a lot of Tuesdays in a row, or a lot of Wednesdays in a row, or a lot of Fridays in a row. And it tends to happen where more people miss Fridays or Mondays than other days of the week. So you have to be careful. Likewise, if you were trying to find how many people attend a movie theater and you want to randomly sample that, you would probably not want to randomly ask them or want to randomly pick every 7th day, because that's not going to get you a good representation of how many people attend a movie theater in a given week. So if you pick Friday and then go every 7th day, that's going to be more highly attended than any other day. You're going to be overrepresenting the sample. So that's what it's talking about with repeated patterns. Systematic sampling is pretty good as long as there's no repeating patterns. Convenient sampling is bad. Don't do it. It's really informative. You can never generalize it to another population. And that's often what happens when you poll on the internet or you just ask your friends. So convenience sampling is not something that you can actually generalize, and it's not a good sample because there's often much bias in convenience sampling.